So today's lecture is on mass wasting, which we also call mass movements, and landslides. These terms are all pretty interchangeable. And this photo here is showing a landslide that happened at the coast following the 2010 earthquake near Haiti, or in Haiti. Okay, so you had a failure of part of the coastal materials where a whole chunk of this coast material here, the cliff, fell down. So we'll start off with this video clip from the National Geographic. So I will play that now. So what is mass wasting? It is the downslope movement of material due to gravity. And again, it's also called mass movements or landslides. So Earth's surface materials like soil or regolith have a certain amount of strength for holding themselves together, and we call that shear strength. If the force of gravity overcomes the shear strength of a material on a slope, then the material can move downslope. So here we have some diagrams related to shear strength. So the gravity is pulling vertically down, and your shear strength is related to friction. So this piece of rock has friction with the piece below it, and that friction holds this piece here. If you were to increase the steepness of the slope, then gravity could start to overcome that shear strength, and then this material will slide downhill. And also, when you're talking about, let's say, a pile of sediment, the sediment grains have friction between the grains, and that friction holds the grains together. If there's water in between the sediment or the rock layers, or if the slope is steep enough, then that could aid in overcoming that shear strength, and then the mass wasting could occur. Okay, so if it were to rain a lot in this area, the water would act like a lubricant and remove, take away that friction, and then the materials will slide downhill. So we have this term angle of repose. That is the steepest angle that a slope can be without the material collapsing down slope. So this is related to shear strength. So again, the sand grains in this pile of sand are compressing against each other, and the friction there is helping the sand grains stay up in this hill rather than just all falling down as a flat layer on the ground. So the angle of repose that dry sand will take is actually 30 degrees. Okay, so dry sand will form a 30-degree angle in a hill. Now, sand that is slightly damp has a greater angle of repose because the moisture in between the sand grains helps the sand grains stick together, and that's due to water tension. Okay, so we're only talking about damp though, like slightly damp, right? But so then you're able to build sand castles because the water tension in between the sand grains helps the sand grains stand up more vertically. So it's almost a 90-degree angle of repose. When sand becomes saturated though, the water acts more like a lubricant and you get more of a slurry where the wet sand acts more like a liquid. And that's because the sand grains are no longer having friction in between them. So then the angle of repose will be low in saturated sand. Then you get more just like a puddle, a flat puddle of this wet sand slurry that forms. So there are different factors that affect mass wasting. The angle of the slope of the land, vegetation on the land, the water content of the materials, the underlying geology. For example, how does the dip orientation of rock layers underground affect how probable a mass wasting event is? And triggering mechanisms. And then I'll go through all of these. So slope angle. The angle of a slope is a major factor of mass wasting. So the steeper the slope, the less stable the land is due to gravity. So flatter land is more stable. The materials are more stable versus steeper land, the materials are not as stable. Then we have a term oversteepening. So erosion can cause a slope to become steeper than the angle of repose of the surface materials. And then that could lead to failure of the slope, which means materials can fall downhill. So what causes oversteepening? Streams, waves, and excavation. So here's a diagram showing a hill and a stream. And then I have the stream has cut into the hill. It has caused erosion. So that's like a steep mini cliff area now, right next to the river. Okay, so that's due to erosion. So now the materials that make up this hill have been cut into with this steep slope. And it makes the whole hill unstable. So especially, let's say if it were to rain a lot, then this material would get saturated and heavy, and then you would definitely, or not definitely, but you would most likely have failure of this whole slope. Okay, and that's because the river has oversteepened part of the slope. Okay, so eventually you may have a whole chunk of the land slide down into the river. Then we have undercutting related to wave erosion. So here waves are cutting into the coastline, and then it makes the upper layers of the rock unstable because you're removing materials down here. So it makes it unstable up here. And then here just, you have failure of the materials at the coast. So in this case, you just have rocks falling down. And then here's another example of undercutting related to wave action. So here, the waves at some point came up and cut into the sediments here at the coast. And then you actually had failure. And now what used to be a road going across here has now collapsed. Part of this has collapsed. So it's not the best idea ever to have houses like this right at the coast, especially when you have soft sediments that make up the coastline. and it's a higher elevation, okay, like just looking at this, you can tell it's pretty vulnerable to landslides. And then you have these houses right at the edge. So that's not really the best idea of an area to have houses. Then we have highway excavations. So when you're going to build a highway, they cut into mountains and hills and they make a flat area to make the road. But when you do that, you're leaving steep areas right next to the road. And then those steep areas, you could just have rocks falling down. Or in this case, you had failure of unconsolidated sediment. So perhaps in this area, there may have been a lot of rain. And the rain, again, interrupts the shear strength of the materials of a slope. So in this case, it kind of just fell downhill. Okay, then we have vegetation. Vegetation makes land more stable because the plants absorb water from rain. So if it were to rain a lot and you have a lot of plants on a slope, the plants will help remove some of that water from the materials, like the soil, for example. So then you have less water actually just sitting in the soil, which would make it more easy for a landslide. But also, the roots of the plants help stabilize the soil. And that's because the roots help bind the particles of the soil together. Mass wasting can occur if vegetation is removed by human activity. For example, logging. Logging is when you go into an area like a forest and you cut down a lot of the trees to sell the wood, like as lumber. But also natural activity like fires, wildfires, can also remove a lot of vegetation. So for example, the wildfires that tend to occur in California result in frequent mass wasting events. That's because of the widespread clearing of vegetation. So sometimes after you hear about the wildfires in California, sometimes you'll hear later on, you'll hear about landslides occurring, okay? Because you don't have the plants holding the soil together. And then we have water content. So increasing the water content of soil and sediments that make up a slope will decrease the stability of the slope. That's again because the saturated ground is going to be less stable. And that is because, number one, you're increasing the weight of the materials that make up the slope. You know, water is heavy. So when you add water in between the sediment grains, it's increasing the weight of all of that material. And then also you're decreasing the friction between the grains. Again, the soil, sand, whatever unconsolidated materials you have. You decrease the friction when you add water. And that acts like a lubricant, allowing the materials to slide. Now, furthermore, if you have clay will be slippery and heavy. So if you have clay layers, it's also a major cause of landslides. So this is a landslide triggered by heavy rain in La Conchita, California. So La Conchita is located at the base of a steep sloped terrace. Heavy rains and irrigation of an avocado orchard contributed to the landslide that destroyed 9 homes in 1995. Okay, so you have an avocado orchard and they irrigate the crops there, but also you had heavy rain. So all of that caused a landslide. And you can see this is all loose, unconsolidated sediments. Okay, it's not hard, solid bedrock. So it makes it easier for the materials to fall down the slope. And the landslide landed on homes at the base of the slope. And then this I showed you really early on in the semester. See, it happened in January. So you had, this is also in California. So along the coast in California, it's pretty steep slopes. Actually, that was part of the lab that we did when we did shorelines. Part of that lab was looking at the California coast and seeing that you have steep cliffs along the coast. But here we're looking at it and it is loose sediments. Okay, again, it's not hard, solid bedrock. It's cliffs made of loose, unconsolidated sediments. So in this case, there was a couple of days of heavy rain in January, and then you had failure of this part of the cliff, and there was a road that went across. Okay, again, this would not be a good location to have houses. You don't want to have houses right on this cliff here because it's loose sediment. And then besides that, you also have waves down here hitting into the base of the cliff. So those factors combined could lead to a landslide. Okay, and here is another picture of that. And you can watch the drone footage as well. And then here are a couple of other photos. So you can see from high above, this is what the road looks like. And then here is the failure. And again, you can see that the waves basically hit into the base of the cliff, making it more unstable. And then that heavy rain made it heavy and it reduced the friction and the shear strength. And then you had failure. I don't know, this just looks like an area where I don't think a road should even be because it's loose, unconsolidated sediment next to a cliff at the coast. So I wouldn't be surprised if this kind of event happens in this location again, because it's an area that's vulnerable to landslides. And along the coast in California, you have areas that look like just like this, where they have homes near the coast as well. And you saw in the video I showed you a few minutes ago, where you had failure and homes collapsed, right? Okay, then we have underlying geology and slope stability. So if the rocks on the slope dip in the same direction as the slope, mass wasting is more likely. So this diagram represents a river valley with underlying tilted sedimentary beds. So here's the river valley and the water is shown in blue, okay? And you could see these are the beds and they're tilted. So on side B, the slope is this way, right? And the tilted beds, although they're not at exactly the same angle as the river valley slope, they're sloping in the same direction, okay? So you have the river valley slope is this direction, and then the beds are this direction. But it's all basically the same direction, just a little bit of a different angle, okay? So that makes these rock layers more vulnerable to having a landslide, okay? Because they could just, if it were to rain a lot on this land, these sediment layers can just fall down and slide downhill. Whereas side A, whoops, on side A, the slope is this way, but the rock layers are perpendicular to that. So if you were to have a lot of rain on side A, you're less likely to have a major landslide because the rock layers are dipping in the opposite direction, perpendicular. Okay, so side B is more vulnerable to having a major landslide, especially if it were to rain a lot. Because this gray layer, this gray here, I have in the description here, is clay. Okay, so the layer on top of the clay could easily just slide downhill. Clay, again, is slippery. It's also heavy. It holds a lot of moisture. Okay, so that's how the underlying geology can affect how stable a slope is. And then here is another diagram that shows a similar case, but different beds, different valleys. Okay, so the most stable areas are where the slope direction is perpendicular to the bed direction. Okay, so here's the slope and the beds are perpendicular. This is moderately stable, and this is the least stable, is when the beds are tilting pretty much at the same angle and direction as the valley slope. And we have triggering mechanisms. Most mass movements are triggered by a force that disrupts the slope equilibrium. Most commonly, this includes earthquakes, heavy rainstorms, or snowmelt. And then we have the different types of mass wasting events: rock falls, slides, and flows. Slides include slumps and block slides, rock slides, rotational slides. Flows include debris flows, mud flows, earth flows. And these mass wasting events are classified by rate of movement, if it's fast or slow, the type of movement, or materials falling, sliding, or flowing, and the type of material involved. Is it rock? Is it soil? Is it debris? Debris is like a mix of materials. And then we have this nice illustration from the textbook that shows different kinds of mass movements, and they are arranged from slowest on the left to fastest on the right. So solid fluxion and creep, slumping, mud flows, debris flows, rock falls, and rock slides. And you see here in the debris flow, it shows deforested land. So that's what I was saying before with logging. You remove a lot of the trees, it leaves the land vulnerable to getting, to experiencing landslides. Okay, so as we go over each of these different type of landslides and mass movements, you can always look back at this picture. So we're gonna start with rock falls. Now, sometimes you may have even seen a sign on the side of the road that says falling rock like this. So rockfalls are very fast. They are common mass wasting events. They can occur at canyons, cliffs, and road cuts. So they're common in mountainous areas. Now, road cuts is what I was telling you before, like highway excavations, where they cut into a mountain or into a hill to build the road, right? They flatten this part of the land to construct the highway. And it made this land too steep for the materials that are there. So then the boulders just fall downhill. Also, you may have a situation like this diagram where you have joints and fractures in the rock. And then those fractures can get enhanced by frost wedging. That's from the physical weathering part of the weathering and sediment chapter. Or you may have the boundaries between rock layers, which are called bedding planes. And that makes different spots of this cliff more vulnerable to breaking apart. And you form what's called talus. That's a pile of angular pieces that break off of a slope and accumulate downhill. Now, rockfalls can occur after an earthquake. They can also be triggered by undercutting. So in this case, these waves are undercutting, oversteepening the base of this cliff, making the rest of the cliff above more vulnerable to failure. This is a rockfall that happened along the Sprainbrook Parkway, which is in Westchester, New York. And in this case, you have rocks that are foliated in a vertical direction. So there are joints kind of in between, or the foliation rather, is vertical. So especially in the winter, when you have frost wedging, right, where water seeps into the cracks in the foliation and then expands when the water freezes, and that pushes the joints open further, or it separates along the foliation, and then the rocks basically just fall down. Okay, so you have this pile of rocks that fell off of this cliff. Now, luckily for the highway, I don't know if you can see it right underneath here, this is a railing. So you have all of this space here, and then you have a railing, and then you have a shoulder on the highway. So that particular highway in this area is not vulnerable to actually having the rocks fall on the road, okay, because of the amount of space you have. Okay, and then here's another rock fall. This happened in British Columbia, which is in Canada. Then we have slides. That's when movement of material occurs along one or more surfaces of failure. It can involve soil, rock, or a combination of materials. And there are two types of slides: slumps or rotational slides, which occur along a curved surface, and a rock or block slide, which occurs along a planar surface. So we'll start with slumps. Again, this is movement along a curved surface. Here's the curved surface, where you have a rotation of this chunk of land. So the dashed line is where the land used to be. And then you have a failure and a rotation. So you get up here, you get a scarp, and then this kind of just rotates downward. And then at the base, you get like this bumpy area. This type of landslide occurs in unconsolidated or weakly consolidated materials. It's usually going to be related to oversteepening along the base of the slope. And a scarp is a steep area exposed as a result of a slump or an earthquake. In this case, it's related to slumping. Here's another picture of slumping. Again, you have the head scarp, then you had rotation, and then the base has this bumpy look to it, where the land kind of accumulates, right? It kind of like just pushes downward. So you get these bumps at the bottom. And then we have the slides, rock slides or block slides. They occur when rocks move downslope along a planar surface, especially if the rock layers dip in the same direction as the slope. So this type of occurrence is common in Southern California. Okay, and you can see the rock layers, the beds of rock or sediments are, it could be sediment beds or rocks, right? So they are in the same direction as the slope. So, right, pieces of the rock can just slide downhill. And again, this river down here most likely undercut the slope, and it made this material further up on the slope more vulnerable to falling. And then it just slid down. Okay, but you most likely had some sort of undercutting related to river erosion down here. Rock slides can also occur along fractures that are parallel to a slope. For example, Turtle Mountain in Frank, Canada. So you had some sort of fracture that was parallel to the slope, and then rocks slid downhill. And then you can go look at it. There's like kind of a tourist area. You can go look at where the landslide happened. Then we have flows. Flows are when materials flow as a viscous fluid down slope. The speed of the movement of the flow ranges from extremely slow to very rapid. And they could begin as a fall, a slump, or a slide, and then change to a flow further down slope. So types of flows include mud flows, debris flows, and earth flows. Mud flows are fluid and rapid. They can move up to 50 miles an hour. Mud flows contain more than 50% clay and silt, which, by the way, mud equals clay and silt. So like a mix of clay and silt is what mud is. It's also mixed with up to 30% water. So it's wet mud, and it forms a slurry of this fluid mud that's able to flow downhill. Mud flows are common in arid or semi-arid environments, and they're generally triggered by heavy rainstorms. Usually mud flows will follow river channels that already exist. For example, Vargas, Venezuela in 1999, that you saw in the National Geographic video that I showed at the start of the lecture today. Here are some photos of Vargas, Venezuela, following the mudslide. Then we have debris flows. Compared to mud flows, debris flows contain larger particles and less water. So they're going to be more viscous and less fluid. So they're going to flow more slowly. And generally, they do not follow existing river channels. So that's a debris flow. This is another debris flow. Right, you see like the large boulders. It does not look all muddy. It still looks more rocky, okay? Then we have earth flows. This is slow, thick, viscous, wet materials. It occurs more slowly than mud flows and debris flows. Earth flows are common in humid climates on grassy, soil-covered slopes, specifically after heavy rainstorms. So you'll see little bits of slumping in the grass. That's generally what an earth flow will look like, okay? These little bits of slumping. So the slumping will occur at the upper part of the slope. So you'll have these little scarp areas, and then further down slope, you'll have that wavy, bumpy looking land. Here's a picture of an earth flow. This is in Virginia. Okay, so up here you have the scarp, and then down here, it's that bumpy looking land. So that's an earth flow. And this is an overhead view of it. So that's an earth flow. Another type of mass wasting is creep. This is slow, long-term movement of loose materials like sediments and soil down a slope. It is the slowest of all types of flow, so you can't really watch it happen. It's just something that you could see happen because of the effects that it has, but you can't actually watch it happen. It's just a very, very slow. But creep is the most significant in terms of the amount of material moved down slope and the amount of economic damage related to a mass wasting event. Creep is most common in humid climates, and it typically involves an entire hillside. And the evidence of creep happening is tilted trees, tilted poles, cracked roads, cracked structures, tilted structures, like a fence, for example. It is difficult to control as well. So what is it? This is a diagram that shows what creep is. So here is a starting position of a particular plast that we're going to use to illustrate how this works. So in the wintertime, the water in soil will freeze. So basically the soil layers are freezing and the soil expands because water expands when it freezes. So the soil will expand. So the new position of the soil when it's frozen is up here. Okay, like you're adding some inches to the height of the soil, or right, it expands. So now this is where the clast will be in the wintertime with the frozen soil, right? Because it expands out this way. As the soil thaws, the clast is going to sink downward vertically because of gravity, rather than perpendicular to the soil surface. So when the soil thaws, let's say this is a pebble. The pebble is not going to go back here, it's going to go back here because of gravity. And then another winter or another freezing period happens. You know, during one winter, you might have a few freeze thaw periods within the soil. Okay, so then you have the soil freeze and expand again. So now that pebble is over here. And then the thawing happens and the pebble ends up over here. So over time, instead of the pebble being here, it's going to end up over here. So in this diagram, this is about 3 years worth of creep that now the pebble ended up over here. So materials slowly creep down slope. But it's the upper layers that are freezing and thawing, okay? Like the lower layers down here are not experiencing this. So it's just the upper layers that are experiencing creep. So you see like these pebbles down here, you know, deeper down in the soil are not affected. It's just the upper layers. So eventually these particles are going to end up down slope, but these particles are going to stay in the same spot pretty much. I mean, they may move a little bit, but not as much as these. So this affects trees because the trees are going to, the base of the tree is going to kind of move downhill, but the tree wants to still stand up straight. So you get tilted trees, you get foundations that crack, tilted telephone poles, tilted gravestones, and the base of this fence, this is a rock wall actually, but the base of the rock wall is going to start to crack and kind of move downhill as well. So sometimes you have collapsing of rock walls. Then we have solifluction, which is a type of creep that occurs in zones of permafrost. Permafrost is soil that is frozen all year round or most of the year. This occurs in your upper latitude areas, such as the tundra. Okay, so in your Arctic regions, for example. It could also occur in high elevation areas, you know, very high mountains will also get permafrost. So in these tundra areas or, you know, your high latitudes, soil freezes deep down and stays frozen all year round. Again, that's the permafrost. But in the summer, the uppermost part of the soil can actually thaw. So you'll end up with this soggy, wet soil on top of still frozen soil. So the soggy upper layers of the soil could slide downhill on top of the lower layers of soil that are still frozen. Even in the summertime, the lower layers of the soil will still remain frozen. So the upper layers of the soil are soggy and thawed, and they're able to flow downhill. Okay, so this again is solifluction. So you get these solifluction sheets where the thawed upper layers of the soil are flowing down slope. Here's another picture of solifluction sheeting. And here's a road that got damaged related to solifluction. So there are different methods that we can use to help prevent mass wasting events. We can improve drainage in an area, which helps prevent sediments and soil from becoming saturated. We can construct retaining walls, put in screens and bolts, and reduce slopes by benching or cut and fill methods. And then I'll go through and talk about these. So improving drainage. Because water is such an important factor in many landslides, if we improve drainage, it'll reduce the risk of land failure. Because then we will reduce the weight of the slope material by not allowing it to get saturated and maintain the shear strength of the slope material. So you can build ditches, gutters, and drain pipes to move the water. So instead of water flowing all down a slope, you may have some sort of drain pipe further up that makes the water flow out in a different spot so that you don't just have a lot of water passing down a slope. Or if you plant vegetation, that helps stabilize the soil or the sediment particles, so that helps improve drainage also, where the plants are absorbing some of that water from the materials in the slope. Here is a retaining wall where they cut into the base of this hill to build the sidewalk and the road. So they built the retaining wall to keep the rest of the hill from failing and falling onto the sidewalk. If possible, like if there's bedrock, then walls are going to be anchored into bedrock. And then behind these walls, you generally would have crushed rock to help with drainage. Also, they have drainage holes in them so that if it rains a lot and this material back here gets soggy and waterlogged, the groundwater can pass out on, out here. It reduces the pressure on the wall because you won't have a lot of water pressure pushing onto the wall. So here's another diagram. Here's a diagram showing you retaining walls. So you have your crushed rock, generally would be behind the retaining wall. In this case, it's showing trapped debris, showing that it stopped a landslide from covering the road. Here is a retaining wall keeping part of someone's property from failing onto their driveway. This is a steep sloped street, and all the homes on this street all had a hill on one side, and then their driveway was flat, and the people who made these homes, they cut into the hill and built retaining walls so that you could have a flat driveway and a garage that you can drive in and out of, right? So they all have these hills with retaining walls holding the hill back down this whole road. You may also find that you have bolts that are drilled into rock walls, not rock walls, like cliffs next to a road. And you may even have fencing or screens. So here's a screen that was bolted into this cliff. Again, this cliff is formed as a road cut because they cut into the land to make the road. So it oversteepened this land. So you need to protect the road from rockfall. So you put a screen up and they bolt it in. And then your slope reduction. Reducing the slope of the land helps stabilize the materials that make up the slope. And this is because oversteepening is a major cause of slope failure. If you reduce the slope, it helps the land become more stable. And again, we have cut and fill and benching. So cut and fill is when material is removed from the upper part of the slope and then is used to fill in spots at the base of the slope. So this makes the slope less steep. And then it creates a flatter surface at the bottom of the slope where you can build like homes or businesses or whatever. So here's a very steep slope. So I tried to illustrate here that you removed part of the upper slope and put it at the base of the slope. So now instead of being very steep, it's a little bit less steep. And then this, you could even make this even flatter, okay? Depending on how much material you remove from up here, you can put the material down here and make a flatter area. Then we have benching, which is also called terracing. So it's when you cut a series of benches into a hillside. It's kind of like a staircase. So you're building like a staircase into your slope, and it reduces the overall average slope. And also, if you were to have landslides or rock falls, they would only be a smaller scale. In this case, they put wood to make retaining walls on the benching. But if you did not have the retaining walls, if you were to have little bits of failure of the slope, then it would, the failed material would just fall on top of this step. It would not be like an entire hillside that fails. It would just be a smaller scale. So benching is commonly used for steep hillsides in conjunction with drains. Okay, we take that out. Okay, so here again, terracing or benching. So this line shows you where the hillside used to be, and then they built in these little terraces. Okay, so again, if you were to have a landslide, it might just be like this section here that might fail. But then the land here that's flat would capture the failed material. It wouldn't be an entire slope that falls downhill and buries the house. Okay, so it makes it safer. And you get these flat areas where you can build houses on. And then sometimes you would put a retaining wall here. Okay, you may have even seen this in hilly areas. You may have seen benching and retaining walls. And then it allows you to build in areas where before you may not have been able to build on this hill, but by benching it, then you're able to build in more spots. Okay, and then I have a video to show. It shows homes in Washington State after a landslide. And it's March 2013. And let me just explain for a second. March 2014, you also had landslides in the state of Washington. So it's almost a year after the previous slide event. So the interpretation here as to why the end of March seems to have landslides in Washington state. Perhaps it is related to snow melt in the mountains, and then that extra water from the snow melting runs over the loose, unconsolidated sediments, leading to a landslide. Okay, and then I have another video from Wyoming. This is near Jackson Hole. So I will show this to you. So here is a map that shows you landslide susceptibility in New York and surrounding areas. So the red shows you the high landslide incidence areas. High susceptibility landslides and moderate incidence is this fuchsia color. The blue is high susceptibility to landslides and low incidence. And green is low landslide incidence. So you can see areas, you can just take a look. Here along the Hudson Valley is a high landslide area. Okay, and then I have a map of New Jersey, well, parts of New Jersey, showing landslide. You have the blue triangle is debris flow, the black triangle is rock falls, the red is rock slides, and the green is slumps. So you could take a look and see where different areas are that have rock slides and so on. Now over here, you're gonna have your areas such as the Palisades sill, which are going to be related to rock slides and rock falls. And then here's all of New Jersey. The key here was kind of small, so I made it enlarged here. So the black dots are debris flows, red rock fall, blue rock slide, and green is slump. So you can see mostly the northern half of New Jersey is where you would get any form of mass movements, right? You don't really have that occurring in the south. So you can take a look, see if you are interested in any of these particular locations. Okay, and then also it tells you the type of rock and how old it is in those areas. Okay, so again, along here, rock slides and debris flows and rock falls. And again, that's related to the Palisades, Jurassic, diabase, the Palisades sill. Okay. So that is the end of the mass wasting lecture.